Hey, hello everyone, thank you for being here today. It's a great pleasure for me to show you some of the first preliminary results of an ongoing project that I have with Scott Edwards about the genomic base of coloration in this fantastic group of birds. So a common observation in nature is that phenotypes are often correlated with the environment. So this is a famous example of how different mice vary their coat coloration in response to different environments in which they inhabit. In birds that have their coloration based on solely on melanins, this is a fantastic phenomenon to study as well. So first of all, we need to know that there's two different types of melanins. We have eumelanin, that is the one that confers that black, dark, gray coloration, and we also have pheomelanin, which is the one that confers the brown, rufous coloration. And one thing that is important to know is that these melanins are produced inside our bodies in these cells called melanocytes. And just to make a long story short, these different kinds of melanins are produced in the melanogenesis pathway. And basically, they're just by tweaking different compounds in the process, either one of these two melanins is produced. And so, there's some general rules about how melanin is deposited in feathers in birds. And these have been described as a geographical rule that seems to hold very well across birds. And so, we're just looking at a figure here where we have on the x-axis temperature, on the y-axis we have humidity, and the general patterns that we've seen in nature are as follows. When in warm and humid places, there's increased deposition of both types of melanins. In warm and dry places, there's increased deposition of pheomelanin, which in turn produces birds that are overall brownish and rufous coloration. In those places that are cold and dry, there's decreased deposition of both types of melanin. This is known as Blocher's rule, and the genomic basis to this process is yet to be fully understood. A fantastic group of birds to study this process is this family known as the antbirds in family Thamnophilidae. I'm talking about roughly 250 species that are restricted to the neotropics. They range from southern Mexico to northern Argentina. They reach their highest vertically in the Amazon. And when you think about antbirds, actually you're thinking about humid, lowland, tropical forest birds. As you can see, there's some variation in plumage patterns and plumage coloration. And there's a handful of species that made it into the dry habitat of South America. These dry habitat specialists are scattered throughout the phylogeny. You can see them in red here in this tree. They occur roughly in these four main regions: northern South America, the Tunisian region in Peru and Ecuador, the Caatinga in northern Brazil, and the Chaco. And these places look pretty much like this. They're just very mesy environments, very highly seasonal, very dry. And we've been able to perform some comparative analysis using complete phylogenies and spectrometric data. And basically we've shown that there's a tendency of having dark phenotypes associated with humid and dry, and humid and less seasonal environments, whereas those lighter birds tend to occur in dry, more seasonal environments. So it seems that Blocher's rule holds up pretty well in this group of birds. So with these two ideas in mind, our recent goals are twofold. The first thing that we want to do is we want to identify the underlying genomic mechanisms driving plumage differences between dry and humid habitats. And we also want to assess whether there are any common genetic mechanisms that might explain, to some extent, convergence both at the phenotypic level and at the molecular level. For today's purposes, I'm only focusing on protein-coding genes in the melanin pathway. And so to do that, I'm focusing on a subclade of the whole family. These are commonly known as anthrax. For those of you that know the birds, these are birds in the genus Thamnophilus, Saccharus, Discitamus, Ursulabus. Species in this genera exhibit all different kinds of plumage patterns. There are species in humid forests, species in dry forests. So it seems like a very nice route to start this whole process. And so for that, we generated reference genomes. For today, I'm talking about 8 reference genomes. We can see here summary phylogeny of the species for which we have reference genomes at the time. We see that we have 3 independent transitions into dry habitats. We see that in these transitions we have sister-human pair relationships, and we have the following genomes. Just some summary information about these genomes. You can see that some of them are more continuous than others, but in general, these all provide information for, good enough information for protein coding sequences and so on. And so just to jump into the results right away, we analyzed information for 63 orthogroups that have been reported in birds as protein coding genes in the melanin pathway. For 15 of these orthogroups, we didn't recover the complete sequence for at least 2 birds. So we did not analyze them any further. We saw that 17 out of these 63 groups showed no variation at all, meaning that this protein sequence across all species was exactly the same. And in 31 of these orthogroups, we actually found a good amount of variance. And we can see that summarized in the following slides. And so the one thing that we did is we use this software called Protean. And basically what it does is just actually predicts whether the protein sequence of a protein has any sort of functional effect. And basically what you do is you just provide a reference sequence. We use the ancestral likelihood estimated sequence for the whole plate, and we basically ask, is the sequence of the species going to be functionally different from the ancestor? So we did that, and Protean, what it does, it gives you a score. It gives you a score that basically ranges from negative to positive values. And basically, but then how do you know whether there's a functional difference or not? Then Protean gives you a score, and it sets a threshold, in this case minus 2.5 and 2.5. If values are above either of those 2 numbers, you can make some inferences about potentially functional differences in these proteins. And so we see that most of our variants are neutral, but there's some that fall below and above these thresholds. And so we see that in 31 of these genes, all of the variants that we found were neutral, meaning that there's some variation, but they don't seem to have any functional effect. And we found that in 17 of these genes, there's variants that might have some functional effect in this. And I want to pull down these results to 2 general statements about what we found. The first one is that most variants seem to be independent from habitat preferences, meaning we have some variation, but they don't seem to match with habitat. And so, just to illustrate this, I'm going to show you an example of DCT, the dopa-chromatoptemerase. This gene is heavily known for having an effect in vertebrate coloration. Mutations in the gene have been shown to produce lighter phenotypes in mice, cows, other vertebrates. They basically reduce the deposition of eumelanin and increase the deposition of eumelanin, meaning that birds seem to be lighter, brownish. And this is what we found in BCT. Basically what we have is that the ancestral in position 280, we have basically a 1 substitution in 1 amino acid. And basically we see that there's no match between habitat and the sequence, but rather we have some sort of allogenetic effect going on. However, there's 2 variants that might have some sort of convergent sequence. And those two genes are as follows. The first one is RAP38, which is a protein that regulates membrane transport of tyranase and TRP1, which are basically critical enzymes in the process of production of eumelanin. And in this case, we found that the 3 out of the 4 species restricted to dry habitats seem to have this huge 19 amino acid deletion in their sequence. Whether this is true or not, it yet remains to be tested via other methods, more sequencing PCR, we need to double check this result. But at least it's some sort of an interesting result at this point. The other one is this gene SLC2285. The SLC genes is a family of genes that seem to be evolving in the melanin pathway vertebrates. It is not clear yet at this point where in the whole pathway this specific gene takes part. But basically what we see is that, again, the three out of the 4 species in dry habitats seem to have this insertion of 5 amino acids. Again, we yet have to check whether this is a true result or not, but at this point it seems to be at least suggested to have these protein coding genes as candidates in the whole process of non positioning. So to summarize, I hope to have been able to show you that variation in protein coding genes is widespread and it's primarily neutral in this group of birds. There's at least 17 genes involved in the melanin pathway that exhibit variation that can be predicted to have some sort of effect in protein function. And there seems to be a couple of genes to have some sort of convergent pattern of evolution into dry habitats. In the future, we have yet to do other things. We are expanding this analysis into including 14 reference genomes of the family. We're of course going to look into regulatory regions, look at genome-wide patterns of divergence, not only focus on protein coding genes. We're really keen to running some functional assays on these protein coding genes that we found as having some sort of structural variation. We're also running some studies and doing some studies about interspecific genetic variation. There's some species that actually vary finely in different regions of South America. So for those we have holographic sequencing data across the cline, coupled with phenotypic data, and so we also do that. Also for one species we've been collecting molting feathers from different bioregions, and so we're just looking at whether there's different gene expression patterns in black feathers, white feathers, brown feathers, and so on. And ultimately, we also want to test whether, we want to look into which are actually the behavioral and ecological mechanisms that ultimately may drive these differences in between dry and humid habitat birds. And with that, I'm happy to take any questions.
So in the Protean software, when you're scoring about the functionality, I was just wondering, how did you get the ancestral protein sequence?
So that's something I got to do beforehand. I did it using this program Filobot.
Sorry?
You have to do it. Protean doesn't do it for you. You have to do it separately, and then you just provide the sequence to Protean, and basically it just performs the test. And it does it by exploring databases like SPI and sample and so on. It uses all that information to actually predict whether that change that you have is functional or not.
So there will be some differences based on there's a single amino acid change in the ancestral, which might not be correct. There might be some uncertainty associated with that.
Yes.
Okay.
Could some of the substitutions character displacement related?
I don't know. I'll have to think about that. Character displacement meaning between species. I don't know. These species, one thing that I should have mentioned is that these species are not sympatric. They're just all in alpha in different regions of the continent. So I don't think that's very likely, but I'll have to think about the processes behind these changes that we're seeing.